Hi, welcome to our practice test that we're going to be doing for test one of Organic Chemistry 2 here in the spring of 2026. We're just getting started. We've done spectroscopy and kind of spent a good amount of time doing, just arrow pushing, curved arrows, talking about nucleophiles, electrophiles before we really start diving into more reactions as we go along. This test is on a lot of that stuff in addition to kind of an in-depth dive on tetrahedral intermediates and what that means for uh, reactions going forward. So, uh, I'll say page one of every one of my tests has kind of conceptual questions. So, questions that are not really reactions, they're not really necessarily practical questions that we've done a lot of. These are more, do you understand some of the concepts we've talked about in class? Deuterated solvents, what are deuterated solvents? Um, Number of equivalent protons, that's kind of a question that could pop up. Have a general understanding of how NMRs work. I don't need you guys to be able to design an NMR, but like what waves are used? Why do we use those waves? So they use radio waves. Um, they excite the nucleus of the proton. So that's that's how to answer that question. The magnet aligns the nuclei so we can get a better read of the nucleus. So that all the spins are pointing in the same direction. So those are kind of how to answer those questions. Just read back through a little bit of that worksheet, have a basic understanding of it, know what deuterated solvents are. One thing that's a little bit different this semester is I would say that when I'm thinking of page one questions, when I'm trying to fill out page one with conceptual stuff that I want you guys to know, a good place to look for that would be in the recitation work. So when you did recitations before a quiz, it was often stuff that was tangential to what you were doing on the quiz. Like it was related, but it was usually like one step ahead or zoomed out a little bit. Not as much so far because we've only really had two recitations like that. But still, that's kind of where I would look. I would look at recitations or any sort of problems that I've done in class that there's my background. Um, in class that we haven't done like a ton of practice on. So that's kind of where I'd look for that. All right. So outside of that page one, which tends to be where most people get frustrated because there's not just a ton of practice on it, right? I can't give you the same question over and over as practice, right? There's only so many times I can ask you what an NMR does. But I would look there. I would look at any sort of problems that at the beginning of units, maybe when I'm kind of talking about how things work. So NMR was a big one to think about. OH, NH2, those peaks don't split anything. They're exchangeable. Sometimes they don't even show up. Knowing those kind of things. All right. So arrow pushing. This is just more arrow pushing practice. There's going to be arrow pushing on the test. That's just, can you fill out these arrows, right? Can you understand that this bond is leaving, is being disconnected. This carbon is being disconnected from this hydrogen. The electrons connecting the two are leaving to make this double bond, and we're going to have HBr as well. This is just elimination mechanism. This mechanism is a little bit more tricky. There's a couple of things going on. So when I have a question like this where I'm given the arrows, I would start by drawing the starting materials back out and going arrow by arrow. So here, the lone pairs from the bromine formed a bond with that carbon very directly. That's what we're seeing here. So I'm going to trace out that bond. That bond has to be there. Then this double bond is leaving. It's being used to form a bond with the bromine. Now, it could be used to form a double bond with that carbon, but that would put too many bonds on that carbon. So the only other option I have is that this carbon is forming a bond with that bromine. And then this bond is breaking and going to this bromine as a lone pair, and it's going to be negatively charged. So just if there's ever an arrow pushing question that you're not sure of, just trace it arrow by arrow. Make sure that that you can explain what each arrow means. Every arrow means something. Every arrow should change something, and nothing should change outside of those arrows. Um,
Question.
what's up?
Does the bromine have a positive charge?
Oh, it
The
does.
left bromine?
Yes.
Okay.
Yeah. I would have lost a point there. Good catch.
I I have a question too.
What's up?
In regards to the first part that you talked about, the conceptual stuff in the test, would that be, I don't know if you're able to answer this, but would it be multiple choice or if, like we write the answer?
I'll go ahead and tell you that the first page, there's two arrow pushing questions. There's one mul one multiple choice question and then one like binary or three, I guess, binary questions. Kind of like true false, but not true false, like yes, no. Um, and then uh a very short fill in the blank, and that's it. If that helps you.
Okay, thank you.
Yeah. So there'll be two mul the binary question, it's kind of a multiple choice. So like I would say there's two multiple choice, two arrow pushing, and a very short answer. Um, yeah, I personally don't believe that knowing what's on the test gives you any real advantage, but it makes you guys feel better. So I'll be happy to tell you how many of each question there are, how many points they're worth. This is a substitution, so this is the second step of an SN1. I literally have to show this oxygen binding to this carbon, right? This arrow has to explain this bond forming. It helps whenever you see a metal to always draw out the ionic bond. Always draw out the ionic bond. So I see a sodium, it's positively charged. The thing it's connected to, the oxygen, is negatively charged. I'm going to draw that out. Make sure every arrow is either coming from a bond or a lone pair. If there's an arrow coming from an atom and you're not showing a lone pair, then I can't, like, there's probably something wrong there, right? So notice every arrow I'm drawing is coming from a bond or a lone pair. Um, so here, first thing I do is always draw out the ionic bond. Um, Not even gonna look at anything else. I'm gonna make that very clear that that's where the electrons are. I have a negatively charged oxygen. That's a good source of electrons. So, um, the other thing I want you to note here, this is kind of a derivative of a question that was on the quiz and all the arrow pushing stuff. This is something that's I think people find tricky no matter what. Note something. There's two hydrogens here. There's only one hydrogen here. There's two lone pairs here. There's three lone pairs here. When people, dang it, when people get this question wrong, I find that they're so worried about this bond that they miss the other important stuff. The electrons from this double bond here don't actually come from this double bond, even though they're near each other, even though they're next to each other. That goes against the flow of electrons, right? Note that this oxygen is actually gaining electrons, but it's not gaining a bond to anything. So the only place it could possibly gain electrons from is the double bond it's connected to. So I know that straight up, which would put a positive charge on this carbon, which would give it room to form a double bond. I also have to explain one of these hydrogens disappearing. That's almost certainly coming from this oxygen taking the hydrogen. And then since there's electrons holding this carbon to this hydrogen, I have to explain that those electrons are actually the electrons that form the double bond. Note that I always have a flow of electrons going from start to finish, right? I can trace, without picking up my pen, all of these arrows without backtracking or anything like that. There's always a flow from beginning to end. The arrows are never going to go in different directions from one source. When I say that, I don't mean different directions as in this arrow goes down and this arrow goes up. Like cardinal directions don't matter. These are three-dimensional structures that exist in space. What I mean is that within the scope of this molecule, everything's kind of get flowing that way. Everything's going to push towards this oxygen, make that oxygen negative. Um, this was a typo. You can't do this without some sort of acid. Doesn't matter what acid it is. So I should have made an announcement about that earlier. I hope some of you guys caught it because what's the big difference between the starting material and the final product? It's actually the inverse of the one above it. I mean, we can see that this oxygen loses electrons, right? It goes from three lone pairs to two lone pairs. And we can see that this carbon gains a proton. So let's deal with the carbon gaining a proton first. Um, this carbon has no lone pairs. This hydrogen has no lone pairs. So I can't just have a lone pair go out and form a bond like I did here, right? Or like I do a lot of times. The only extra electrons that this carbon has is from this double bond. So it has to use electrons from the double bond to make a bond with that hydrogen. But that means that this carbon is losing out on electrons, right? Because this carbon is taking the electrons from the double bond and using it to form a bond. So this guy's losing electrons. So I'm going to backfill to form that double bond with the oxygen, which also explains why the oxygen loses a lone pair and becomes neutral. So that's my bad on the acid base on the acid here, but these are almost the exact questions that we're seeing in quiz 1. Lithium is a metal. So what happens here is one thing I can immediately see is that this terminal carbon loses a hydrogen. I have to explain that, and I have to explain the formation of a double bond. So I have to take that hydrogen and collapse it to form that double bond. Again, this is the second step of an E1. So for whatever reason, I found that elimination mechanism are kind of hard to see. So I like asking them because they come up. They're important mechanisms for a reason. All right, I see a metal. I'm going to draw out the ionic bond, not even think about it. This case, what I'm doing, I recognize that O-ethyl, that this piece is this piece in my final product. So mapping out where different pieces are on the final product is always helpful, no matter what kind of question I'm asking, whether it's an arrow pushing or a reaction question or a synthesis question. It's always good to think about that. This is a substitution. I need that ethyl to make a bond with that carbon because it is bound to that carbon in the final picture. And then this OTS, even if you don't know what it is, it's a good leaving group, so I can just show it leaving. It needs to leave anyways because it's not a part of the final product. Um, this is just a sodium hydride question. So sodium hydride, I'm going to draw that out. And I noticed that I form H2 gas. So this hydrogen is going to form a bond with this hydrogen, leave its electrons on the pyridine, which you don't need to know the name of, but all right. This is a ring opening question. So again, it's useful sometimes to draw out kind of the starting materials and to say, all right, this whole MgBr didn't go anywhere. So these electrons had to have been attached to this carbon, right? That's Mg gave the electrons to this carbon. So that had to be the case. So it's really that carbon. So I'll go ahead and number 1, 2, 1, 2. That's binding to this carbon. And then I have to explain this arrow that breaks this bond. So that bond is broken. and that oxygen gains electrons. So just going arrow by arrow. So I know that the carbon one has to bond to that middle carbon. I know that that bond between the oxygen and carbon has to break, and the oxygen gains electrons. This one's a pretty simple carbonyl addition. So nothing on this side changes. All of this is just surface dressing. This turns into an OH because this nitrogen used its lone pairs. Non-negotiable. There has to be a bond between this nitrogen and that carbon because there's an arrow there. And I think where most people would get points off here would be missing a positive charge on the nitrogen. So that's arrow pushing. Um, Pretty straightforward, but I need to make sure that you guys are really good at the basics because we're going to push arrows all the time, every day. So we need to be able to understand the language, and I need to be able to see that you guys have mastered the language. All right. So now we're on to nucleophile, electrophile, and the first two steps. So step one is going to be acid protonates what? Nobody?
Like,
Electrophile or what?
mm, or base the protonate. I mean, base the protonate the nucleophile.
Yep. So either acid protonates electrophile or base deprotonates a nucleophile. So in this case, I have what's clear to me as a nucleophile. I see an electrophile on this carbon, and I see an acid. I'm going to go ahead and write HA out, just because H2SO4 can kind of be annoying to deal with. So step one, since I have an acid, acid protonates electrophile. Boom. So that's what I have. That's step one. Step two is nucleophile attack electrophile. Where people might run into issues here is they might see the positive charge on the oxygen and want the nucleophile to attack that. That will not happen. No matter what the carbonyl is, no matter what's going on, no matter where the charge is, the electrophilic part of a carbonyl is always going to be that carbon, the carbon of the carbonyl. No matter what, I'm attacking the carbon of the carbonyl and pushing electrons up into that oxygen. So this is the second step. This is nucleophile attack electrophile. Then at this point, it's just counting electrons. Making sure that I have all of my atoms in the right place. So one thing I like to do is to number my atoms, make sure that everything's in the right place, make sure that I connected the right thing to the right thing, right? So the nitrogen should be connected to atom carbon 2. Carbon 2, which is here. Carbon 2 is connected to carbon 1 and carbon 3 and 4. So everything's in the right place. I've double checked my charges. Nitrogen has 4 bonds, so it has to have a positive charge. Oxygen has gained electrons. It has 2 bonds. It's neutral. So where people are going to lose points here is one of those three problems usually is they'll either add to the wrong spot on the electrophile or they'll drop a carbon or a charge. So don't let that be you. Don't lose easy points on easy things, right? Double check yourself. You should have time to do everything. Um, don't spend your life on, there's gonna be two NMR questions. We're 20 points out of 80. That's a decent amount, but there's a lot of partial credit to be had. I'd rather you do your best on those, set yourself like a time limit on each one. I'm going to work as much as I can, but then make sure that you give yourself time to go back through all the other questions and just make sure you haven't made any sort of dumb mistakes with how many carbons you have or how many charges you have. Because while there's two questions worth, um, I don't need you to show the conjugate base of the acid. Well, there's two questions worth 20 points of like 20 total points of NMR. There's like 3 or 4 questions worth 6 points of this, right? So like losing points here when you shouldn't, make sure that's not what you're doing. All right. I see a metal. I'm going to draw the ionic bond. I'm not even going to think about anything else. That's the first thought. That's a base, sodium hydride, pretty classic base. Um, so just to make sure everything's right, I'm going to use my base to deprotonate my nucleophile. OTF, OTS, these are common oxygen leaving groups. So I put one of the two of them in the chart every day. So I want you to recognize this as a leaving group. That's something that you may or may not have been taught in Organic 1, but it's good to recognize. So after the deprotonation of my nucleophile, I have a negatively charged oxygen. Step 2 is nucleophile, attack electrophile, kick off leaving group. Nothing else about my molecule changes, except that now my oxygen has kicked off the triflate. And I've done a substitution. All right, so this is an intermolecular question. So this is one way I can make something a little bit tricky. If you got to the end of the electrophile nucleophile basics worksheet, you did a fair amount of these. So even if you didn't feel like you needed to do all of the nucleophile electrophile worksheet, if this problem was a problem for you, there's a part at the end of that worksheet that might be worthwhile going through. But essentially, you can have your electrophile and your nucleophile on the same molecule, right? It's totally possible. There's nothing wrong with that. Happens all the time. I have a metal, so I'm going to draw out the ionic bond. And since this is a base, there's a metal present. It's going to deprotonate my nucleophile. So I'll just go ahead and draw it out so we're super clear. Base deprotonates nucleophile. Then second step is nucleophile attack electrophile. This is where you might run into trouble. 1, 2, 3, 4, 5. So that ring is going to be 5 big. So whenever a molecule attacks itself, it's going to form a ring. I count that this oxygen is going to be part of the ring because it's attacking this carbon. So I'm going to have a 5-membered ring with one of those members being an oxygen. I see, let's just say this is 5, 4, 3, 2, 1. 5 is connected to 4, 3, 2, 1. Nothing on 4, 3, or 2. There is an oxygen that's negatively charged on 1. Cool. Got a base. I've got a nucleophile. Got an electrophile. Nucleophile gets deprotonated to form the negatively charged version. Then nucleophile attacks electrophile. Then I form a tetrahedral intermediate, which on this test, I'm not going to have you do all of them. Like I'm not going to have you start from the beginning, do this, and then do the tetrahedral intermediate. It's going to look just like this practice test where there's going to be some parts where you're doing the first 2 steps and some part when you do just from the tetrahedral intermediate forward. But going after this test, that's what we're going to be doing. We're never going to split them up again. It's always going to be the full mechanism.
I have a question.
What's up?
For the one that you just did, because I know it says to circle the best leaving group and box the best kicking group. Um, in the product, would the leaving group be
Oh, yeah. I haven't been
would
doing that.
the
I'll do that.
oh sorry.
No, you're right. No, let me go back and do that.
Okay, thank you.
Um, yeah, so I do want you to be able to recognize when you have a tetrahedral intermediate. So tetrahedral intermediates, these happen when you add into carbonyls. So in this case, I did add into a carbonyl. So I have a tetrahedral intermediate. So I need to box the best leaving group, which is going to be this OH, or circle the best leaving group. And the only thing with electrons that could possibly be a kicking group would be the nitrogen. With this reaction, um, I didn't add into I had a leaving group. I didn't have a carbonyl, so there's no tetrahedral intermediate here. There's nothing to do here. In this reaction, I did add into a carbonyl. So I need to look at the best kicking group and the best leaving group. In this case, what added in this would be the only thing that could be a leaving group. Because if I look at this, a carbon, and a negatively charged oxygen. So this is a Ti, and there's no leaving group or kicking group here, right? The carbon, the negatively charged oxygen, the hydrogen can't be a leaving group. Um, Likewise, in this circumstance, because this is negatively charged, and this was my nucleophile, that's not a leaving group, that's not a leaving group, that's not a leaving group. And my nucleophile can't be my leaving group. So this is my tetrahedral intermediate, and there's no leaving group here. So I can't do anything.
Question.
Yes.
For the last one that you did, how did you know that there was no leaving group? Like, I'm just confused on how to understand that it can't leave. Like, how did you know that it just got added?
Because
Like that. Oh,
I just added it.
okay. So the nucleophile is the one that just got added.
Yeah, the nucleophile cannot be the leaving group. Because imagine if I were to collapse this back down and kick this off, I would just get right back here.
Yeah.
Right. So we're just not
Okay.
gonna, that would go in a circle.
Okay. Thank you.
Yeah. So it is the nucleophile. It's the thing that just added in. This cannot be a leaving group. That's the thing that I always like highlight in red, or on the test, it's gonna be bolded on the test because our printers only do black and white. But yeah, that's the equivalent of this, right? This is what just got added in.
I have a question.
Yeah.
I understand what you're saying about how it can't be the leaving group because that's the nucleophile that attacked and it was just added. But can you explain how, like, even though it can't be the leaving group, can it be the kicking group and then the O minus be the leaving group?
It could, but O minus can't be a leaving group.
Why not?
I would make it O2 minus. Not gonna happen.
Oh, okay.
Yeah.
Okay, thank you.
Yes. Because when things leave, they take more electrons. So negatively charged oxygen. That's why a positively charged oxygen can be a good leaving group, but a negatively charged oxygen will never be a leaving group. Yeah, good question. I'll actually see
I have
that
a
here.
question.
What's up?
I'm still confused of how to identify the kicking group.
Okay. Leaving group. Halogens, then OHs or OH plus, then OR, then NH, NR. So that's leaving groups. You do this first. So leaving group gets priority. Second is the kicking group. Oh, wait, I did this backwards. Sorry. I did the kicking group. OH and RNH. So with leaving groups, we prefer to have a carbon on the thing. With kicking groups, we prefer not to. So if it helps just to have this list, like do the leaving group first, halogens, then oxygens with carbons on them, oxygens, OHs, NRs, NH, then assign the kicking group. And if nothing fits into either one of those categories, you can't find a leaving group or a kicking group, then there's nothing you can do in the tetrahedral intermediate.
With the kicking group, my TA had said that O minus goes before OH. Is that correct or is that
Yeah,
incorrect?
that'd be correct. Yes.
Okay.
Hi, I have a question.
What's up?
I was wondering if you do not draw out the ionic bond on a metal question, would you lose points?
Probably. Yeah. Um, especially at this point, I would do it. I'm less worried about like this, where I have to draw like this bond out between an oxygen and hydrogen. Like I'm okay with you shortcutting that a little bit, but I don't want you to just draw a line from NaH. I need you to know where that line is. Like I need to know where the electrons are there. So yes, I care that you have the habit of drawing out the ionic bond, and I will grade as such.
Thank you.
Yes. All right, so I've done the protonation. So it seems like with a lot of you guys, these first two steps are not the sticking point, but the point here. When we get to the tetrahedral intermediate is where we get a little bit stuck. So in this case, this is what just added in. This cannot be my tetrahedral. This cannot be my leaving group. Then I'm going to look. Do I have anything that looks like that left attached directly to this carbon? Has to be connected to this carbon in particular. So I have an OH on it. I have a hydrogen, a phenyl. The OH would be my best leaving group. So I do have a leaving group. And this oxygen would be my best kicking group. It's the only oxygen remaining. So once you get to the tetrahedral intermediate, try to assign best leaving group and then best kicking group. And we'll do more practice here. There's several. All right, so this is just, I'm giving you a tetrahedral intermediate, and we've got to get to the final product. So this is acidic conditions. I can tell because it's positive, there's a positive charge. So I'm going to have to do a proton transfer. This was just added. Well, I actually don't have to do a proton transfer here. This was just added. So it cannot be my leaving group. So that means that this is my leaving group. And this would have to be my kicking group. So we do the proton transfer to get the positive charge onto our leaving group. In this case, the positive charge is already on the leaving group. So the proton transfer has already happened. So at this point, I just need to collapse and kick. So the goal of the proton transfer is to get the positive charge on my leaving group, which I've done.
I have a question.
What's up?
So you always know that you need to do a proton transfer whenever you see a positive. No, whenever you like it's to get the positive charge. So whenever you don't see a positive charge, that's when you do the proton transfer. Is that what
Whenever
you're saying?
whenever we're in acidic conditions, you need to do a proton transfer. So we need to get the positive charge onto the leaving group, which has already happened here. So to be
Okay,
honest,
thank
this is
you.
kind of just a poorly written question. In acidic conditions, you do a proton transfer. Here, the proton transfer has already been done. I would take this proton away and give it right back to the leaving group because that's where I want the proton to be. We don't just shift protons around because it's fun. We shift protons around to get them to the leaving group. And since the extra proton's already on the leaving group, here we don't need to worry about it. Um, the methyl was just added. That's not a leaving group. That's not a leaving group. That's not a leaving group. There's no leaving or kicking group here. Someone asked, under basic conditions, can we assume there's water? We can use like acidic conditions. You can at the end. I can show you what that might look like. You probably don't need to though. But you can only really assume that at the end because you don't need to do the proton transfer. This is basic conditions. So there's no proton transfers. There's not an extra proton to go around. So this is pretty straightforward. This is my best leaving group. This is my best kicking group. So since I'm in basic conditions, I don't have to do a proton transfer. I can just collapse and kick from my kicking group and get this. You can see in basic conditions, a lot of times it just works itself out, right? I don't need water to deprotonate anything. There's nothing going on here. All right, this is a better question. This is acidic conditions. I can tell because it's positively charged. Anytime there's acidic, I need to do a proton transfer. This can't be my leaving group, so it's between this nitrogen and this oxygen. This oxygen is my best leaving group because oxygens are better leaving groups than nitrogens. And this oxygen is my kicking group because oxygens are also better kicking groups than nitrogens. So the nucleophile that just added in cannot be a leaving group, but it can be a kicking group. So I need to do a proton transfer. So I'm going to assume there's water here. And my goal is that right now my kicking group is positively charged. I'd like to make my leaving group positively charged. So I'm going to take the proton from my kicking group because we have extra protons because we're in an acidic environment. And I'm going to give that extra proton to my leaving group. So that's my proton transfer. It happens over 2 steps. I take it from wherever it was and I give it to the leaving group. Then I collapse and I kick. And in this case, what that does, if I follow my arrows, and let's say this is confusing because you've never seen this happen with a ring before. Just do this like you would do any other arrow pushing question, right? This is why we practice arrow pushing so much. This oxygen forms a double bond with that carbon and gets a positive charge because it lost electrons. This bond breaks, not all those bonds, but that bond breaks, and this positively charged oxygen becomes neutral. Nothing else changes about this molecule. This is kind of an ugly looking molecule right now. You'd be right if you kept it like this, but I like to redraw it, so I'll just say 1, 2, 3, 4. So I have an OH with 1, 2, 3, 4 carbons, and then a carbonyl with a nitrogen, and then 2 carbons off of it. So that's just a prettier way to draw it.
Does it matter which way we end up drawing it or no?
As long as it's not too ridiculous.
Okay.
Like if I can tell what everything's connected to, um, This is on the borderline of too ridiculous, like this bond being like that.
Yeah.
I would rather you, like if if you don't want to draw it back out as a line, you can draw it out like this. Just kind of fold that oxygen down so the nitrogen has room.
Okay.
That's another way to do it.
Thank you.
Um, yeah. Again, we have acidic conditions, positive charge. So I'm going to do a proton transfer. Um, find my best leaving group. It can't be what I just added. So it's either this oxygen or this nitrogen. So oxygen OH is a best leaving group. Then my best kicking group again is my nucleophile, that just added in. So I've got to take the proton from the kicking group. In step 2, I'm going to give it to the leaving group. So I make my leaving group a better leaving group. So that was my proton transfer. I've got my proton on the leaving group, which is what I want. Then I collapse and I kick. And I get that. All right. I want to impress on you guys that these two things that we're doing here, this will be the rest of the semester. If you guys master this, if you get really good at this is stuff that we will keep coming back to. This isn't stuff to cram right before a test. This stuff I want you to understand, I want you to think about, I want you to be able to do and be proficient in because we're going to keep doing it. Some of the NMR stuff we're going to be less likely to come back to. It's still good. I would still know how to do the NMR, but like this is key stuff for this class. We're building a foundation.
Question,
What's up?
quick question on the second to last one that we just did with, I'm just confused because nothing leaves.
This alcohol leaves.
But isn't that alcohol on the left?
Yeah. It's no longer part of this carbon, so it left the carbon.
Oh, okay. Got it. Thank
Yeah,
you.
it doesn't just evaporate into dust. It's kicked out of the molecule or kicked out off that carbon.
Okay, that makes sense. Thank you.
Yeah. Even a leaving group doesn't truly leave. It's still like sitting in solution, right? Conservation of mass and all that. It's just sitting as like a Br minus, you know? It doesn't just like disappear. All right. So carbon NMR. Going to draw a line at 100. This is my SP and my SP3 carbons, and this is my SP2 carbons. So I have one SP3 and 4 SP2. So I can pretty much quickly eliminate a lot of these just with that knowledge. There is symmetry here. That would give me 1, 2. This is 2 SP3s. So off the bat, it can't be that one. There's no symmetry in this next molecule. So 1, 2, 3, 4. 4 SP3s. Can't be that molecule. Again, there's no symmetry here. 1, 2, 3, 4 SP3s. So it can't be any of those. This one has symmetry through it. So there's only one SP3. It has to be this molecule without even looking at the SP2s. So if you forgot, SP3 are carbons that are that are not a part of a double bond, right? So a carbon that has 4 different things attached to it. I don't know why I have a rainbow going on my screen. SP2 carbons are part of double bonds, generally. It's a pretty quick way to identify them. All right. A few syntheses. So I look at this final product and I say, I formed an ether. I formed a reaction between these two things. So I'm going to start thinking from that point. I'm going to work backwards. Um, I can either cut this here so the alcohol is on the right, or I can cut it here so the alcohol is on the left. I'm going to cut it there because what it does for me is that on one side of this cut, I have my alcohol, right? I have this group. On the other side, I have a leaving group on this carbon. It's ultimately going to leave. So this gives me two targets to work towards. This is called a retrosynthesis. We've worked backwards from the final product to say, what are some targets that we need to get to? So clearly, if I want to make one, it's going to have to start from this starting material because this is a starting material that has 3 carbons on it. The other one has more carbons, so it cannot be the starting material for that. So I need to get an OH on the middle carbon. Right now, I've got a Br on the end carbon. So in order to move the heteroatom, I have to first eliminate it. So in this case, I need a bulky base since a primary leaving group. And then I need to add an OH to the middle carbon. So that's a Markovnikov OH. I can use H3O plus here. So that gets me to my first piece, piece 1. Likewise with piece 2, I need to eliminate this OH the way, well, I'm going to do this the right way. I'll explain why I'm doing it the right way. If you do it the faster way, you might lose a point or two. So I want to turn this OH into a leaving group. So I'm going to just substitute it out with bromine first, because that gives me more options. If I just try to eliminate this alcohol, I will only get the more substituted elimination, because I can't use a bulky base to remove this alcohol. But I can use a bulky base to remove that bromine. So it's a little bit annoying, but putting a leaving group there gives me a little bit more flexibility. All right, now I can use a bulky base to do the elimination from this side instead of from this side. Now I can do the addition anti-Markovnikov, HBr, H2O2, to get this. All right, which is 2. Having 1 and 2, I can react them together with some base and get my final product. Do you guys have any questions about synthesis? The half sheets the other day seemed to be pretty good about synthesis. I think you guys are getting it for the most part. I mostly use synthesis to really get you guys to just go back and practice some of these organic 1 reactions. Markovnikov additions, anti-Markovnikov additions, eliminations. And so what I would say is if you're struggling with these at first, maybe have that reaction chart in front of you while you do a few practice problems. And then as you do them, the practice, you should start to memorize them. But you should try to force yourself to look at that reaction sheet less and less.
Question.
Yes.
So when you use an acid and heat, that would only give you the most substituted double bond, right? Which is why we can't use it here.
Yeah, so if I used this, that's what I would get, and that would get me further away from getting the bromine on this end carbon.
Okay, thank you.
So it's one of those things where if you did acid and heat and jumped straight there, you'd still probably get 8 or 9 points out of 10. You know, you might lose 1 point for like, all right, that's kind of inaccurate, but like I would, if you forget PBR3 and you just know how to do that, just do it,
Is there a way to remove the OH group and get the less substituted double bond or no?
Not directly that I know of.
Okay.
There's a couple of different ways to like turn OH into a leaving group and then do it or something like that. But not directly.
Okay. Thank you.
There might be some there's almost certainly some designer way that some organic chemist knows how to do, but I'm not sure. Um, I'm actually going to pause the recording and come back in a second. I've got to run to the bathroom really quick. Sorry about that. Let's do one more synthesis because it's all kind of the same steps. We kind of see the same things over and over. Here, again, I'm making that cut. So I have this alcohol. We actually have the same targets for this one. So I've got to make one. I've got to make it out of this. So likewise, I'm going to, in this one, I can use H2SO4 and heat to get me that double bond. And then again, Markovnikov OH addition to get here. And then with this one, it's actually just faster. I can just use a bulky base to get here, and then an anti-Markovnikov OH addition to get here. So someone asked if we can use if we can turn OH into a leaving group and then use one of the bulky bases to get elimination. That's what I did here. I turned OH into a leaving group, bromine. The problem, you can't just, it's as good of time to talk about as any. So you might be tempted to say like, could I protonate this with some acid and then use a bulky base This doesn't work because the bulky base would just take that proton and we'd get right back. Reactions don't tend to work in basic and acidic conditions. Like as soon as you add a base, it's going to take any protons sitting around. Um, so that would just kind of go cyclical. You either do reactions in acidic conditions or you do reactions in basic conditions. When you add an acid and a base, it just kind of neutralizes things and nothing happens. So that is what we do. I just use PBr3 to turn it into a bromine. So these are the steps. I mean, that's a good question, right? It's something that might be intuitive, but it just doesn't work. Let's see. Is there anything? There's nothing much new here. It's kind of the same thing. So I think we're going to move on to NMR because that's probably where most people are stressed, struggling. I'm gonna be honest, carbon mass spec, I wouldn't spend much time on. I would jump straight here and say I have a carbonyl definitely, and I have an OH. There's
I have a
three
question.
oxygens, but
I have a question.
yeah.
I know that you just said that mass spectroscopy and CNMR you wouldn't worry too much about because for this question, like I only pretty much use what you were just talking about with the OH and the carbonyl, but like if like needed, like I'm just kind of confused about like what mass spectroscopy like actually does.
So to be honest with you, this molecular formula comes from mass spectroscopy, right? You can actually see it here. So you get a mass of something and then you can calculate the molecular formula off of that. So that's the main use. I'm just going ahead and giving you the molecular formula. There are some professors that will make you try to figure out the molecular formula based off of the mass. Um, so when people use mass spec, it's either they'll just give you the mass and say, what's the molecular formula? And so you have to kind of guess and check your way to figuring out exactly how many oxygens and carbons there are. Or you can do fragmentary analysis and say like, oh, I've got this fragment at 45, so therefore I know I've got an ethyl group. Um, but it's just kind of faster to go to the NMR and more comprehensive.
Okay, thank you.
Yeah, really, organic chemists, for the most part, use mass spec as like a check. Like, hey, I think I made this molecule. The NMR says it's this. Does the mass spec check out with the mass I would expect this to have? More than we use it to figure out what we have. It's a good question. It's kind of like if you're trying to do a murder mystery, like, I don't know, hair analysis might not be something that's terribly useful except for once in a blue moon, but we still talk about it, you know? Like when I can do DNA analysis and get a ton of DNA information, I'm just going to do that first, you know?
Thank you.
All right, so now we move on to NMR. I'm going to start multiples of three, so I have a three hydrogen doublet. All right, I guess I'll start with this one. What's up?
Dr. Little.
Hey, I'm in a recording. What's up? Yeah,
Yes.
I assume Orgo won. Yeah, I have office hours in 30 minutes.
So you're confused about the practice quiz, but I guess I could come tomorrow.
I'll be out as soon as I can.
Okay, thank you.
So I have a three hydrogen triplet, so three hydrogens, and I know that that three hydrogens has two next door neighbors because it's a triplet. So there's two neighbors. Then I look at the rest of the graph. This isn't two hydrogens, this isn't two hydrogens, this is. I only have one other thing that's two hydrogens big, right? So this has to be these black hydrogens. They have three neighbors, so there's no additional neighbors here. So I've checked off these two peaks. They're done. I accounted. My goal is to account for every single peak on the NMR in as few of chunks as I can, right? Pair them together as much as I can. This is a CH3. And I know it's a doublet, so it has one neighbor. So that one neighbor has to be this peak. I know that because this is an OH peak because it's broad. Right, look how wide it is. And OH peaks don't split. So I have my CH peak looks to be a quartet. So it has three neighbors, so that checks out, right? I'd expect this blue CH to have three neighbors just based off what this is. So that means I don't know what is left on this CH. And I know I have an OH. So I've checked this off. I've checked this off. I've checked every part off of my NMR. So before I move on, I'm going to double check my chemical formula. C5H10O3. C5H10O3. I have 1, 2, 3, 4 carbons. So I'm missing a carbon. I have one oxygen and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 hydrogens. That can't be right. Oh, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. So I'm not missing any hydrogens. I'm missing a carbon and an oxygen. I know I've got a carbonyl. Oh, I forgot to do this. 2 times carbons plus 2 minus hydrogens all over 2. 10, 12 minus 10 is 2 over 2 is 1. 1 degree of unsaturation, which is explained by my carbonyl. I'm missing one more oxygen. That oxygen, remember, oxygens either come as OHs, carbonyls, or as ethers. This oxygen can't be a carbonyl because I have no more degrees of unsaturation. I don't have another carbon. It can't be an OH because I don't have another hydrogen. So this has to be an ether of some kind. Do we have to worry about NH2 peaks? You should be able to do NH2 peaks. They're the same as anything else. There will not be an NH2 peak on the test, but you should be able to do them. There will be an NH2 peak on a future test. Probably. So these are all my fragments. So this is an end piece. Carbonyls have 2 pieces coming off of them. So this is a middle piece, a middle piece, a middle piece, and an end piece. The alcohol, because there's only one thing coming off of it. So that's how I like to think about it. It gives me a place to kind of start. And then when I start putting together, that's when shifts really come into play. So, my blue 1 hydrogen peak, he's pretty far downfield. He's connected to, he's probably connected to an electronegative atom because he's between 3 to 5. Likewise with this 2 hydrogen peak. He's probably connected to a 2 hydrogen, 3 hydrogen thing. So, sorry, what am I talking about? He's likely connected to an electronegative atom. So I'm going to put this alcohol on one of these two R groups of this CH. Because that would um, kind of solve two problems. It would put this OH somewhere as an end, right? That would make sense. And he had two groups to put on, so this makes sense to me. This kind of turns this into an end piece now. All right, and so now I have two end pieces and two middle pieces. So I can either connect this oxygen directly to this CH, or I connect this oxygen to this CH2. Well, it makes more sense to put it next to the CH2 because the CH2 is also pretty far downfield. And so that CH2 is probably also next to an electronegative atom. So that would help me explain that. So as I build my chunks bigger, I remove them so I don't double count them or anything. And now I only have two end pieces and one middle piece. So there's only one place to put this carbonyl, and it's between these two pieces. So CH3CH with an OH off of it, then a carbonyl, an oxygen, and an ethyl. This would be my final product. Now, I made some assumptions there, definitely. To be honest, I haven't done this question in months, so I forgot the exact answer, but I know how to do these problems, so I can kind of get to an answer pretty quickly. The two assumptions I think I made that might be hard for people to wrap their head around is how I knew that this OH went here. And that's simply because it was an end piece, right? So I couldn't have really put it over here. Like if I have an ethyl and I put an OH right here, the molecule's done, right? I couldn't add this to anything else. And OH ends things, right? So it made sense to put it in a place where I would still have somewhere else to build off of. Likewise, this oxygen being here allowed me to continue building off an end piece while putting this carbon next to an electronegative atom. So I find when people, the jump from getting an 80% on a NMR question to a 100% on an NMR comes down to recognizing that these are between 3 to 5 and have to be near, they had to be near heteroatoms. That's the only explanation to why they're that far downfield. Does that make sense? Have I lost anybody? Have I lost everybody? All right. Well, I'm moving on. How many of these do I have? Two? Okay. Oh, this one's got a chlorine. Fun. Degree of unsaturation, 2 times carbon plus 2 minus chlorine, minus 9, which is hydrogen. All over 2, 16 plus 2 is 18, minus 10 is 8, divided by 2 is 4. So I'm thinking benzene immediately. Question mark. You can kind of see the chlorine here, so that's pretty typical of a chlorine on a mass spec. We showed that before. Even just a brief glance, this kind of validates that I probably have a benzene, right? There's a lot of sp2 here. but I'm not going to worry about counting them or anything like that. Again, SP2 here. So this is just a zoom in of this region. Helps me kind of see things. I'm not going to worry about the complex splitting here. This looks like a doublet to me, and this looks like a triplet. There's some like, you can kind of see that there's some weird complex splitting if you zoom in, but I'm not going to worry too much about that. So I have a 2 hydrogen doublet and a triplet, and then 6 hydrogens as a methyl. So I definitely have a benzene, right? This screams benzene. And I have a tri-substituted benzene. There's 3 things on it. So let's try it 1 hydrogen at a time. So if that hydrogen was a triplet, that means it has 2 neighbors, right? If I look at that one, that means that this hydrogen would be a doublet, this hydrogen would be a doublet, and I have potential symmetry here, right? Well, I have necessary symmetry because I have this 2 hydrogen peak. These have to be symmetrical to each other. The only thing I'm missing at this point is 2 CH3s that also have to be symmetrical to each other. So the only places I could put those CH3s so that they're symmetrical to each other would be here and here. Because if I try to do something like this, well, now that wouldn't be a singlet anymore. It would have a neighbor. So there's a methyl here, a methyl here. The only thing that I'm missing when I look back at my formula is a chlorine. And so that chlorine is here. And that's my final answer. So that's NMR, that's tetrahedral intermediates, that's some basic organic 1 synthesis, low carbon NMR stuff, arrow pushing. Before I head off, I have office hours in 15 minutes, so I've got 15 minutes to talk. Do you guys have any questions? Is there anything else you want to go through? Anything pressing on your mind that you want to have recorded for everybody else to see?
Yeah, I have a question.
What's up?
Is it possible for anything with a positive charge to be a kicking group?
Is it possible for anything with a positive charge to be a leaving group?
Kicking group. There was a question earlier that had one like that.
So yes. So like here, this was my kicking group. Even though it has a positive charge on it right now.
Okay. So you have to do a proton shift if
So
that is the case.
Well, anytime there's a positive charge, you're going to do a proton transfer. So sometimes that positive charge is on the kicking group to start with. We need to get it on the leaving group.
Okay, yeah, thank you.
Yeah, that's a good question. Someone said for NMR, what are some specific peak patterns we should recognize? To be honest, you can do it the way that I've done it here, which is just start building fragments. Like just that is like the way to do it concretely, right? You build up a fragment 1 peak at a time. You check off that you've explained every single peak on the NMR. That's a good way to go. There's going to be a little box at the bottom of these questions. It's going to look like, it's going to say like degrees of unsaturation, and then it's going to have your molecule, like draw your molecule in that box. That way we know what we're grading. What I'll say is, let's say you got to this point, but didn't know where to put the OH, didn't know how to put this, didn't know where to put this. Create a molecule that has all of your fragments. Put them together the only way you can put them together and put that in the box. The only thing that will be graded is what's in that box. So make each peak, make each fragment, Make sure you can explain each fragment and then put them together any way you can. If you don't like, if you are lost to the point of like, how do I put them together? Put them together the only way you can. So there's no more R groups. Make sure that every fragment that you know is on the NMR is explained in this box somewhere as like a real molecule. Don't just draw a bunch of fragments in here. Draw a real molecule that has your fragments in it. This is how you'd get the most partial credit possible. Then, like it, so that would be like base level, like we're doing NMR for the first time. What people do as they get better with NMR is they start chunking information. They start seeing groups and patterns that are common, right? When I sit here and I do this, I I can draw this. I can do this whole NMR in my head. I don't need to draw it out. I draw it out for you guys because I want to show you guys a thought process that works to get the right answer. But I've done so many of these that I've chunked the information into bigger patterns. So the question you're asking is good. If you want to save time, if there's things that like, which I would suggest you do, it gives you more time for everything else. It gives you more time to check everything else. That quiz I put on Canvas a couple weeks ago has the major patterns, right? Um, I would look, if I've done that quiz and I've internalized it, I would see this 3 hydrogen triplet and this 2 hydrogen quartet and know without a shadow of doubt that I have an ethyl group in my final product. And that ethyl group is probably connected to an oxygen because it's so far downfield. Like, boom, I could draw that immediately. Like, just in 10 seconds, I would know that oxygen, carbon, carbon. Because I recognize that ethyl pattern. That's a big one. Like for this question, that ethyl pattern stands out. That's an easy one. The other things I'd have to start thinking about a little bit more. Well, I have a 3 hydrogen doublet, right? But even that is a pattern you start to see. 3 hydrogen is one neighbor. So seeing an ethyl, seeing isopropyl, those pop up a fair amount. Seeing just a methyl, you know, um, those save time, right? You just can draw it. And that's honestly even how we grade it. Like when I'm giving partial credit for a NMR question, I'm gonna say like, hey, you've got an ethyl here. You have an ethyl next to an oxygen. Boom. That's 2 out of 10 points. So you get degrees of unsaturation, that's 2 points. You got an ethyl next to an oxygen, that's 2 out of 10 points. You got 4 out of 10 points, and that's all you knew. 10 seconds worth of work, right? The other major pattern, which is something someone just asked, is do you need to be able to draw benzene as orthopara, etc.? You don't need to tell me that it's orthopara, but like recognizing that doublet as a para substituted benzene as a benzene with our groups here will save you a lot of time. So you're not sitting there being like, what do I have to do? Or, you know, if I see a singlet in the benzene ring region and there's 4 protons, I know that I've got a meta substituted benzene, right? Because that's a singlet. Just immediately, boom, I can draw that benzene with the right substitution pattern. Done. Like, saves me so much time. So those are that's why I posted that 2 weeks ago, because if you get good at those patterns, you just look at these things and you're like, oh, that's a benzene ring that has one thing on each side, or that's a benzene ring with 1 hydrogen between two different groups, right? Meta substituted. So that's a really great question and gets to the heart of like as you get better, the goal is that you see these patterns right off the bat, right? They're not something that you're having to sit there and draw every little mini fragment about. You can just I've got an ethyl group. I probably have an ester. I have an OH most likely. I can put all those pieces together really fast because I recognize those patterns and see them. So the big patterns are like small carbon containing groups like ethyl, methyl, isopropyl, tert butyl, and the different Especially like di-substituted benzenes are really common, right? So a para-substituted benzene, orthometa. I don't need you to name it. I don't need you to be like, hey, that's a meta substituted. But recognizing when you would see different things, right? This is the only di-substituted benzene I could possibly draw with one hydrogen on it, or with one singlet, with a singlet. Does that make sense? That's really great questions. Any other questions? No? All right. So if we don't have any other questions, I'm going to end this recording. I'm going to hop off. I have office hours in 6 minutes now. So feel free to stop by and say hi. I'm in Carruthers Hall, 218, and I will see you guys there.
Thank you.
Thank you. Bye.
Yeah, the video should take it's going to take a minute to get up. So it might not be up till kind of early afternoon.